Welcome back, everybody. So in this lecture, we're going to talk about numerical integration. In other words, can we do some clever tricks to make it easier to, well, integrate? Or another way to think about this, because of how we started out defining what an integral is to find areas. So it turns out, of course, the obvious way to find the area between two curves is to do the integral. But then what if I get an integral I can't do? This hasn't come up for us very much yet, but it turns out there are lots and lots of functions. In fact, if you picked a function at random, you would discover that essentially all functions are such that you can't write down an antiderivative for. Now, this may seem really weird because we haven't seen any of these in the homework. You'll see what to do with some of this in Calculus 2. You'll see ways of finding antiderivatives for things you might not otherwise be able to. I'll give you an example. Think about e to the x squared. E to the x squared, right? So the squared is is on the x. Okay, that's a function that you try to do substitution. You realize that doesn't work. That function doesn't have an antiderivative that you can write down in a nice way. So if you wanted to integrate it, or if you asked your calculator to, what does it do? It does one of these numerical tricks. It tries to find area, right, by doing something clever to figure out area with geometry. Let me show you what I mean. So the way we first talked about finding area, right, when we were first discovering what an integral is, we said that the area there should be the definite integral between a and b of f of x. And how did we do that? Right? Well, we were talking about the definition of an integral, which means breaking things up into little pieces, pretending the height was constant on each piece and adding up all those pieces, then taking the limit as we use more and more pieces. So if we had to do this without being able to find an antiderivative, maybe we just try to add up the rectangles by hand and hope we get close. Right? And in this picture, of course, I'm adding up rectangles using left endpoints, and we talked lots about that in the previous videos. So I'm using the height of my rectangle to be the height at the left side of every subdivision. So, for example, if you look there at A, right, I've got a rectangle that runs from A over a little bit more to a breakpoint. And instead of assuming that the height is, well, as anything I might assume that it is, I'm going to assume that the height is equal to the value at the left side of that interval. In other words, the value that it is when it starts there at A. Then in the second breakpoint, I use the height equal to whatever the height of the function is, again, at the start of that endpoint on the left. And I get these various rectangles. Of course, I'm going to be missing some stuff, right? I mean, I can find the area of each of these rectangles because I know the height of each of those rectangles, and the width is going to be delta x. I can find those areas and add them up, right, in all these different breakpoints. But I'm missing a lot when I do that, right? So maybe there's a better way to do this, right? So we're going to think of this sort of as like our first try at finding the areas by just breaking it up into rectangles and adding up the rectangles. And for a formula, right, what we would do is we would take the delta x times each of those various heights, right, and get the area of each rectangle and add them all up. Or what I could do if I were actually going to do this by hand, instead of saying f of x0, in other words, the height at the left-hand endpoint, times delta x plus f of x1, which is the height at the next endpoint, times delta x. Let's just factor the delta x out. Say that makes it easier. Then I can just multiply by the delta x once at the end. So that helps a little. But still, I've got to plug each of these endpoints into the function, then add all that up, then multiply by my width that I've factored out to get the area of each of those rectangles added together. And that'll give me a good answer, except you notice that I'm definitely missing a lot. So this works, but I'm going to be underestimating in this example by a lot because my function is increasing as I go along. Using the left endpoint misses some stuff. I could try using the right endpoints, but that's going to be an overestimate, again, in this case, because my function's increasing. Now, if my function were increasing part of the time and decreasing part of the time, it wouldn't be quite so bad, because sometimes that overestimates and that underestimate. But you see that trying to use just the right endpoints or just the left endpoints, we might get too much area, we might get too little. So if I break this up into lots of little pieces, say 6 in this case, right, and I find the width of each piece to be my delta x, then I plug in now the right endpoint. So instead of starting at f of x0, I'll start out by looking at f of x1, because that's the height at the right endpoint of the first interval, making my first rectangle. And so I have f of x1 times delta x, and then f of x2 times delta x, and so on. And I'll add all those up. And again, to make things easier when I'm actually plugging this into my calculator or calculating these numbers, I'll factor the delta x out, so I only have to multiply that once. So this is another example, right? This is another way of doing it, and I'll get an answer that's kind of close, but obviously I'm getting too much area here. So could we do something with some geometry to make this a little better guess? Because you notice what the problem is, right? You can sort of see in this picture, I'm overshooting, right, by that green part that's sticking out above the red curve. In other words, what I'm doing is I've got those little, well, they look kind of like triangles. Now, they're not exactly, because the red curve is curved. It's not a straight line. But it kind of looks like I'm getting triangular-shaped pieces that are too big. And, of course, when I was doing the picture with the left endpoints a minute ago, I was missing some triangular-shaped pieces. Again, they weren't perfect triangles because my red graph there is curving, and so it's not a straight line. But maybe I could do some geometry and take advantage of that. What if I had some sort of a wiggly looking graph in general there? What if I were to not to break things up into rectangles, but I broke things up into trapezoids? So instead of picking the height at the left endpoint and making a straight line across to make a rectangle, or picking the height at the right endpoint and making a straight line across at a constant height to make a rectangle, what if I drew a line between the left endpoint on the graph and the right endpoint on the graph and sort of made a triangle at the top, right? You see, that's going to be better, right? In fact, it's going to be a lot better because I won't undershoot or overshoot quite the same way. I'm getting closer to matching the actual graph because I'll just, make that little extra triangular piece on top. So I need to figure out how to find the area of a trapezoid. And if you haven't done geometry for a while, and I'm suspecting most of you haven't, may not have thought about what the area of a trapezoid is. But the way a trapezoid works is you take to find the area, you find the base, length of the base, that's my delta x, and you multiply it by, well, it's the average of the two heights. So in other words, you take the value of the function at one endpoint and the value of the function at the other endpoint and average those together. That is the area of my trapezoid when I multiply that by the delta x. So if I were to go through and do that for the first piece, the second piece, and so on, you notice that what will happen is some of those are going to get doubled up. In fact, the very first endpoint and the very last endpoint, right, don't get used twice. But all the ones in the middle do, because they show up as a right endpoint and a left endpoint, depending on which side of the breakpoint you're on. So when you're done with all of that, you'll have the function at all these various points, right, times my delta x, and also times the 1/2. The 1/2 comes from the 1/2 in the area of the trapezoid formula. So that looks more complicated to actually sit down and do, but this trapezoid rule is going to be a much, much, much better fit. Okay? So let's write this out formally. If you have a continuous function from a to b, then you can find an approximation to the integral using the trapezoid rule, and it's that formula we have there on the screen. Again, so what's my delta x? Well, we're using evenly divided subdivisions. So if I'm integrating from a to b, then I find the distance from a to b, which remember, I have to subtract the big number minus the small number, so that's b minus a, divided by n, which is how many subdivisions I'm taking. That tells me how long each subdivision should be. Okay. So that will be my delta x. Okay. Of course, as I use more and more subdivisions, if n gets bigger and bigger and bigger, then I'll get a better approximation. And this is going to be a pretty close approximation. Right? In fact, if you look at this really closely, what you see that I'm really doing here is I'm averaging together the left-hand endpoint rule and the right-hand endpoint rule. In other words, this trapezoidal rule is the average of the first two that we did. Okay, so far so good, but still, it's closer, right? In other words, I can get a closer approximation to the integral by by not having to do quite as many subdivisions. But how close is it? Well, glad you asked. Well, we can figure out exactly how close we are because we have a way to measure the error. Now, it's ugly looking, but it's not that bad. It's nice enough that it gives us some way of seeing how close we are. If your function has a continuous second derivative, so you have to be integrating something that's not just continuous, but it has a derivative and a second derivative, and that second derivative is continuous. So that's asking for a lot. Although most of the functions we've been dealing with, you know, that'll happen. If you have a continuous second derivative and m is the biggest that second derivative ever gets, or the absolute value of it ever gets, on my interval, then how far off will I be? Well, there's the formula. En is how far off I will be in estimating my integral by using the trapezoid rule. And that'll always be less than b minus a cubed over 12n squared times m. So where does this come from? That's a great question, and I would love to tell you, but we're doing Calculus 1, not numerical analysis. So I'll just at this point say that if you take a class in numerical analysis, and you should, because you get to learn all kinds of cool things like this, then you will try calculating things using shortcut tricks like the trapezoidal rule here. And depending on the function and what you know about it, you can go through and estimate how far off you are. And so this is a really, really handy thing. So we can ask questions like this. Suppose I need to approximate, get an answer for the integral of 1 over x between 1 and 2. Okay, now, obviously you're looking at this going, oh, well, I know the right answer, right? When I integrate 1 over x, I'll get log of absolute value of x, right? So the right answer for this is log of 2 minus log of 1. Okay? And log of 1 is 0, so the answer here is log of 2. Yes, but what's the log of 2? Well, I just plugged that in my calculator. Oh, really? Where'd your calculator get that? Oh, there's a log fairy, right? There's some sort of magical elf that lives inside my calculator that tells me how to calculate logs and trig functions and so on. Well, no, it doesn't work that way. What happens is, if you need to know how to calculate a trig function or a log or something, then your calculator has to have a way to do it. And there are ways to do this, and this is what you study in numerical analysis, is these different ways to compute things, and we're getting a taste of that here. So suppose that I need to get the right answer to within 2 decimal places. So in other words, I need to be within 0.01. So it's like plugging this into a calculator, but I only have 2 decimal places on my calculator. That's how your calculator lies to you all the time, right? I mean, if a normal calculator maybe displays 8 decimal places, right? Well, it's calculating the answer that you're asking for, but it only cares about getting the first 8 decimal places right. The answer that it's calculating is not the right answer. The answer it's calculating is close enough so that it gets the first 8 decimal places right, shows you that on the screen, and you don't know the difference because the screen doesn't show any more decimal places than that. So this is like doing this with a calculator with, say, 2 decimal places, and as long as we get to within 2 decimal places, the person pushing the buttons won't know the difference. So then our question is, how many intervals do I have to use? Because the more intervals I have to use, the more of a pain this is, right? They have to break things up into pieces. So let's see. What I need to do to use my rule is to see how big the second derivative can be. So if my function is 1 over x, the derivative will be, well, think of this as x to the negative 1 power, so the derivative will be negative x to the negative 2 power. The second derivative will be, well, negative x to the negative 3rd power times a 2 for bringing down the exponent. So in other words, 2 over x cubed. Again, now that may look a little weird because we're so used to doing integrals now, everybody's forgotten how to take a derivative, but this is taking a derivative, not integrating, right? And we take the derivative twice and we get 2 over x cubed. Now, is that a continuous function? Not at 0, because I'd be dividing by 0, but on the interval from 1 to 2, sure, it's fine, nice and continuous. So then you can say, what's the maximum value of 2 over x cubed on that interval? Well, that's a question that we could play with and figure out how big a function is, using what we know about finding the maximum value of a function. And so we could take a third derivative and set equal to 0 and that kind of stuff. But there is an easy way to see what this is. This function is really easy because it's 2 over x cubed. That means that with the x cubed in the denominator, this function is decreasing. It's getting smaller as we go along. So the biggest that the derivative will be is what it is at the first endpoint, at 1. By the time it gets to 2, you see it gets much smaller. I mean, you can just check. When you plug in 1, you get 2 over 1 cubed, which is 2. When I check it at the other endpoint at 2, I'd get 2 over 2 cubed, which is 8. So 2 is obviously much bigger than 2 over 8. So the biggest this thing is going to be is at the first endpoint. And at that spot, the second derivative can be as big as 2. So according to our rule, the error in using the trapezoidal rule to evaluate this integral, rather than just say it's log of 2, right? Because that's the exact answer. That's less than b minus a cubed over 12n squared times this estimate for m. So you plug all that in. The b and the a, that's 2 and 1, right? The m, that's 2. So with all that, we can simplify this a bit, and we get 1 over 6n squared. We cancel the 2 with the 12, and of course 2 minus 1 will just be 1, and we cube that, and we still got 1. So all that stuff on the right-hand side becomes 1 over 6n squared. And I need that to be less than, right, less than 0.01. That way my error will be less than 0.01. And then I just solve that inequality. I take the n squared to the other side, multiply by the 6. That says n squared has to be bigger than 1 over 0.06. And then that's about 16 or so. Take the square root, and that says n has to be a little bigger than 4.08. So if I want to get the answer to this integral, right, to within 2 decimal places, then all I need to do is do the trapezoidal rule, but I need to use more than 4 subdivisions. So I have to break it at 5 places. So I'll start at 1 and go to 2, and I'll break it up in 5 places. And if I do that, I'll get an answer from the trapezoidal rule, and that'll be great because the answer will be right to within 2 decimal places. So this gives me another way of finding out what log of 2 is to within 2 decimal places, just by adding up some values of 1 over x. Okay, well, so far so good, right? We got a slick way of calculating areas by not doing rectangles, but by doing little trapezoids. Maybe I could do a little better. What if instead of drawing a straight line from one endpoint to the other, what if I fit a curved thing on top of my rectangle? In other words, I don't do a rectangle, I don't do a trapezoid. I do something with a curved top. That'll fit my curve even better. What if I try to fit a parabola on top of it? So it's like I take a piece of a parabola and I stick it on top of my region. And because the parabola curves, maybe that fits the graph better. And the answer is you could do that. And if you went through, and now that we know how to find the area under a parabola, because that's the area under a quadratic equation, right? You can go through and calculate what that is exactly. And here's the formula for it. Right? We get 1/3, and then we have the value at a couple different points times the width, which is delta x. Now, one thing that's a little different here is to fit a parabola on top. We actually don't do this between x0 and x1. It takes 3 pieces to fit a parabola on top. I have to do this at x0, x1, and x2. The reason is, well, if you have a quadratic, there's 3 unknowns, right? A quadratic equation looks like ax squared plus bx plus c, right? So I have to be able to figure out the a, b, and the c, which means I have to have 3 pieces of information to figure out 3 unknowns. So I have to fit the curve at 3 places. So I'll have to always have an even number for n, and I'll always fit them in these pairs like this with 3 pieces and 3 more pieces and so on. If you add all that up, then Simpson's rule becomes this. That 4 that shows up in the middle is sort of strange looking. You haven't had a 4 before. But also, if you think about it, at those even pieces, those will get counted twice because they'll get counted from the left side and from the right side. So yeah, let's state this nice and formally here. Suppose you have a continuous function, then Simpson's rule for approximating integral looks like this. You would get delta x divided by 3 times, and then you evaluate f at the different endpoints. But there's this odd pattern of coefficients in front of the x, in front of the f. So you'd have f of x0, then 4 times f of x1, then 2 times f of x2, then back to 4 again times f of x3. And it'll alternate with 4, 2, 4, 2, 4, 2, 4, 2, except that you don't get any coefficients, no extra numbers in front of the first and the last endpoint, x0 and xn. And of course my width then will be, b minus a over n, right, where n's how many of the endpoints I have, and I'll always have to use an even number of endpoints to make this fit, because I'm matching these parabolas that have to come in even pairs. There's also an error estimation for Simpson's rule. Now, it's a little trickier because you have to have a continuous fourth derivative, okay? And if you find the biggest value of the fourth derivative, or absolute value of the fourth derivative, then the error estimate is that the error is less than b minus a raised to the fifth power over 180 n to the fourth times the maximum value of the fourth derivative. Now, you go, okay, wow, that looks awful. But notice that that's an n to the fourth in the denominator. If you have n raised to the fourth, then all of a sudden a little bit of n goes a long way. In other words, Simpson's rule is going to fit really well because a small value of n, when it gets raised to the fourth power, that'll really drive down the error in using Simpson's rule, because those parabolas are curved and they're going to fit a lot better even than just a straight line did. So let's summarize what we have here. We could try to add up an area using rectangles with like left endpoints, and there was this formula that we saw how we did this, where we're just using the left endpoints every time. Or we could do this with the right endpoints, and again we get this formula, and if you look at those, your eyes glaze over. It doesn't seem to mean very much, but notice that what we're doing with the right endpoints is we're starting with x1 and going up to xn. With left endpoints, we started with the left endpoints, x0, and we stopped at xn minus 1 because we always use the one on the left side. The trapezoidal rule looks a little bit more complicated, and it's really just the average of the first two ways of doing things. The average of the left endpoint version and the right endpoint version. So when you write down what you get, you have this nice formula. And then for Simpson's rule, the rule looks a little bit more complicated, but it's not too bad. We have this pattern of 1, 4, 2, 4, 2, 4, 2, 4, 2, 1. We have these coefficients we're multiplying by. And we have this delta x over 3 out in front. So it looks really, really awful the first time you see it. But when you actually sit down and do an example, it's not so bad. So let's try this. Let's use 4 subdivisions. Okay? N's going to be equal to 4. And let's estimate, say, the integral from 0 to 2 of x squared plus 3. Okay? Let's do that with rectangles, with trapezoidal rule, with Simpson's rule. Okay? So with rectangles, right, well, we would split this up into 4 pieces between 0 and 4. That means I'd have to break it at 0, a half, 1, 1 1/2, and 2. My delta x will be a half, right? So that's easy enough, right? Split it up into these pieces. My first break point is at 0, then a half, then 1, then 1 1/2, or 3 halves, then 2. And so I plug all those different values into my function. So I'll keep these up here on the screen as we go. So when I plug 0 into the function, I get 0 squared plus 3, so that's just 3. When I plug a half into the function, I get a half squared, which is a quarter, plus 3, so I get 3 1/4, and so on. So I have these different values of the function at each of those breakpoints. Now I just plug this into the formula for using left endpoints or right endpoints or trapezoidal rule or Simpson's rule or whatever, and see what we get. So for left endpoints, well, my first left endpoint would be at 0. So I would get f of 0 times delta x. Then I would get f of a half times delta x. Then f of 1 times delta x. then f of 1.5 times delta x. Or to make things easier on myself, I'll factor that delta x out, right? And that's how you see it there on the screen. So I have to add all that up, and that gives me 7 3/4. So there's my guess with 4 intervals and left endpoints. Let's try right endpoints. So this time, instead of trying this at x equals 0, right, because that's the first left endpoint, I'm doing this with right endpoints. The first right endpoint would be 3 1/4. And then we use 4, 5 1/4, and 7. Multiply all those by half, and this total comes out to be 9 3/4. So, like a platform. this is a bigger estimate, right? Okay, let's see what we get with trapezoids. So if I use the trapezoidal rule, again, the formula looks nasty, but it's not too bad. Once we've actually plugged in 0, 1/2, 1, and so forth, all our breakpoints into the function, and we have those values written down, we just have to, write all out this whole big long sum. So f of 0, that's f at our first breakpoint, that's a 3. Then we get 2 times f at the other breakpoints until we get to the one on the far right, which is f of x4, that's f of 2, and the value there for f is 7. So I add all those numbers up, I multiply by delta x and divide by 2, and that comes out to be 8.75. So again, if you check, that's exactly the average of the first two ways of doing it, with the left endpoints and the right endpoints. And this is much closer. Okay, let's try this with Simpson's rule. Now, here the pattern is uglier because we have nothing times f of x0, then this 4, 2, 4, and then nothing times the last f of x4. But again, not too bad, right? Once we know what the values of the functions are, we wrote those down ahead of time, we just plug all those in, we add everything up, we multiply by delta x and divide by the 3, and this turns out to be 8.66666 or so. Okay. And so let's summarize how this worked. When we did left endpoints, we got 7.75. When we did right endpoints, we got something that sounds like a Harry Potter train, we got 9 3/4. With the trapezoidal rule, we got something in the middle, which was 8 3/4. And again, notice that's exactly the average of the left endpoint and the right endpoint way of doing things. Simpson's rule, we came out to be 8.6666. Okay. What's the right answer? Well, if we do this with the fundamental theorem of calculus, plug in our found antiderivative and plug in the 2 and the 0, you get 8 2/3, which would be 8.66666, and keeps going. So you see, Simpson's rule is by far the closest. In fact, Simpson's rule more or less got it exactly. Right? So that's because this was a parabola, and Simpson's rule always hit it exactly with a parabola, which is very cool, right? In general, Simpson's rule is going to be very, very close. The trapezoidal rule will be pretty close, and the left and right endpoints won't be all that close, but it's quick. Right? So that's the trade-off in calculating things numerically. So at some point later in your career, you may very well take a class in numerical analysis, or you study computer algorithms. And a big question is, how do I do this as fast as possible? And so this is a first glimpse at thinking through those kinds of issues.